In 1997, on an ordinary summer afternoon, one of the biggest jets in the sky came in for a landing that looked completely normal, right up until the moment it wasn't. The wheels touched, the nose dipped, and then, in less time than it takes to say it, a 400,000-pound aircraft bounced, twisted, and flipped completely upside down on the runway. Fire swallowed the fuselage whole, and somehow, every single person on board walked away alive. The date was July 31st, 1997. The place was Newark Liberty International Airport. The aircraft was a FedEx MD-11 freighter, and the accident report that followed didn't blame a mechanical failure, a storm, or a broken part. It blamed the airplane itself, the way it was built, the compromises baked into its design years before this crew ever stepped into the cockpit. Because the MD-11 wasn't just another wide-body jet. Among pilots who flew it, it had a nickname that said everything: the slam dunk. Because that's exactly how you had to land it. Not gently, not gracefully, but forced onto the runway, hard on purpose, or you risked exactly what happened at Newark. This is the story of how one of the most advanced airliners of its era became one of the most unforgiving planes to bring back down to earth. To understand why the MD-11 flew the way it did, you have to go back to a struggling aircraft manufacturer trying to survive. By the mid-1980s, McDonnell Douglas was in trouble. Their earlier tri-jet, the DC-10, had been dragged through years of bad headlines after a string of serious accidents. Meanwhile, Boeing and Airbus were pouring billions into brand-new, clean-sheet designs. Aircraft built from a blank page with modern aerodynamics and modern systems. McDonnell Douglas didn't have billions to spend. What they had was an existing factory line, a loyal customer base, and one option that made financial sense. Don't build a new plane, stretch an old one. On December 30th, 1986, the MD-11 program officially launched, backed by over 90 orders and options from 10 airlines. The plan looked solid on paper. Take the DC-10. Stretch the fuselage by more than 18 feet. Add fuel-saving winglets. Bolt on modern engines. Strip out the flight engineer station with a new glass cockpit. And promise airlines a genuine long-haul workhorse capable of flying up to 7,000 nautical miles nonstop. Airlines lined up to buy it. What they got, though, was an aircraft shaped less by an ideal engineering vision and more by a company trying to squeeze every ounce of efficiency out of an old airframe on a shrinking budget. And that single mindset, efficiency first, is where the trouble and the flare began. The most important decision in the entire MD-11 program happened at the back of the aircraft. On the original DC-10, the horizontal stabilizer, the wing-like surface at the tail that controls the aircraft's pitch, was enormous, over 1,300 square feet. Engineers on the MD-11 project cut that surface by nearly a third. From a pure number standpoint, it was a smart move. A smaller tail means less drag. Less drag means better fuel burn. And fuel burn is exactly what airlines cared about most when they were shopping for a new long-haul jet. But a smaller tail also means less built-in control. So to make up for it, McDonnell Douglas turned to something genuinely cutting-edge for the time, a computer-assisted flight control system called the Longitudinal Stability Augmentation System, or LSAS. Here's how it worked. The MD-11 had a fuel tank built directly into its tail. During cruise, fuel was pumped back into that tail tank, shifting the aircraft's center of gravity rearward. That reduced strain on the smaller tail even further and squeezed out extra fuel efficiency at altitude. Before landing, the system was supposed to pump that fuel back forward, shifting the balance point toward the nose again and giving the pilots more stable, predictable handling on approach. It was elegant engineering. It was also a trade-off with a hidden cost because the MD-11, by design, was what engineers call neutrally stable. It didn't naturally want to fly straight and level on its own the way older jets did. It sat right on the edge of its own balance, and the computer system was there to hold that edge steady. At cruising altitude, with everything functioning as designed, that arrangement worked beautifully. Down low, in the final seconds before touchdown, it was a completely different story. Landing any large aircraft comes down to one delicate maneuver called the flare. The pilot gently raises the nose in the final seconds before touchdown, bleeding off speed so the main wheels settle onto the runway smoothly instead of slamming down. It's supposed to be predictable. Small input, small response. That predictability is what lets a pilot make tiny corrections in real time without overreacting. The MD-11 broke that rule. Because of its reduced tail size, the aircraft had noticeably less natural pitch damping, the built-in resistance that keeps an aircraft's nose from swinging too far in either direction. In practice, that meant the MD-11 responded to control inputs sluggishly at first, and then, a half-second later, far more aggressively than the pilot expected. Picture nudging the controls slightly, feeling nothing happen, nudging again, and then having the nose snap upward far more than you intended. Pilots transitioning from the older DC-10, an aircraft they knew intimately, found themselves fighting an airplane that looked almost identical but behaved like a completely different machine. They'd correct. The plane would overcorrect. They'd correct again. Aviation has a name for this feedback loop, pilot-induced oscillation, where the human and the aircraft end up amplifying each other's mistakes instead of settling into a smooth landing. Now stack a second problem on top of that. The MD-11 had among the highest wing loading of any commercial jet flying at the time, meaning a huge amount of weight supported by a relatively small wing area. Highly loaded wings need more speed to generate enough lift, which is exactly why the MD-11 came in 10 to 20 knots faster than comparable jets, often between 155 and 170 knots on final approach. At those speeds, mistakes don't correct themselves gently. A bounce doesn't settle down, it gets worse. And then there was the moment right after touchdown, arguably the most dangerous part of the whole sequence. Pilots consistently reported a strong pitch-up tendency the instant the main wheels made contact, the nose wanting to rise again even as the aircraft was supposedly down. If a pilot instinctively pushed forward to fight that rise, the aircraft could skip right back into the air, setting up a second landing, often harder than the first. Put it all together, a sluggish then sharp pitch response, unusually fast approach speeds, and a nose that fought to rise after touchdown. And you get an aircraft that punished hesitation and punished overcorrection almost equally. That's why crews stopped trying to finesse it. They planted it, deliberately, firmly. No soft, graceful flair, just get the wheels down and keep them down. Several airlines built entirely new simulator training programs specifically to teach pilots this one unusual skill, how to land the MD-11 like it wanted to be landed, not like every other jet they'd ever flown. The landing difficulties weren't an isolated flaw. They were one symptom of a bigger problem, an aircraft that had been sold as more capable than it actually was. American Airlines took delivery of 19 MD-11s, expecting a jet that could fly nonstop from Dallas to Hong Kong. It couldn't. The aircraft consistently missed its advertised range and fuel burn targets from day one. McDonnell Douglas launched an emergency 5-year improvement program with Pratt & Whitney, General Electric, and NASA's Langley Research Center just to try closing the gap. And even after all those upgrades, the MD-11 still couldn't hit its promised range at full payload. By 1995, American had given up and sold its entire MD-11 fleet to FedEx. Singapore Airlines went further. They canceled an order for 20 MD-11s outright and bought Airbus 340s instead, saying flatly that the jet couldn't handle their long-haul network. One aviation analyst later called the MD-11's timing classically unlucky. It arrived just as the industry was moving away from 3- and 4-engine long-haul jets altogether, right as new regulations were opening the door for more efficient twin-engine aircraft to fly those same ocean-crossing routes for a fraction of the cost. While McDonnell Douglas was busy trying to patch an aging design, Boeing and Airbus were building the 777 and the A330 from a completely blank sheet of paper. And the accidents kept adding up. A China Airlines MD-11 flipped over at Hong Kong in 1999 during gusty crosswinds. A FedEx MD-11 bounced, rolled, and burst into flames at Tokyo's Narita Airport in 2009. Different airlines, different airports, different years, but almost always the same underlying story, a landing margin that simply wasn't there. By the mid-2000s, most passenger airlines had already retired their MD-11s, replacing them with the very twin-engine jets they'd once been built to outcompete. Of roughly 200 MD-11s ever produced, well short of the more than 300 McDonnell Douglas originally hoped to sell, the survivors found a second career hauling cargo instead of passengers, where specialized crew training could manage the aircraft's quirks, and where its massive freight capacity still made it commercially worthwhile. McDonnell Douglas itself didn't get a second act. Boeing absorbed the company in 1997. The MD-11 program was wound down not long after, with the final 2 aircraft rolling off the line in the year 2000. The jet that was supposed to save McDonnell Douglas's place in commercial aviation ended up marking its exit from the industry entirely. Here's the thing worth sitting with. The MD-11 wasn't a product of careless engineering. In a lot of ways, it was the opposite. Every decision that made this aircraft hard to land was, on its own, genuinely smart. The smaller tail cut drag. The tail-mounted fuel tank fine-tuned the center of gravity for maximum cruise efficiency. The computer-assisted stability system was years ahead of its time. Each piece, in isolation, made the airplane better at flying long distances economically. But every one of those pieces also created a dependency, a system quietly compensating for something the airframe could no longer do on its own. And dependencies have a way of revealing themselves exactly when you can least afford them. In the final 30 seconds of a flight, at high speed, close to the ground, with almost no room left to react, McDonnell Douglas built a jet that was remarkably efficient at 35,000 feet and genuinely difficult to put safely back on ground. Every trade they made to win efficiency in the air quietly cost them stability at the runway. And in aviation, the runway is always where the truth catches up with you. If you found this one interesting, hit subscribe for more deep dives into the aircraft, the decisions, and the disasters that shaped modern aviation. Thanks for watching. I'll see you in the next one.